Alright, let's get through this Features of Functions 5.8. So we're taking a look at the domain, range, and whether it's a function. So when we're just given a group of points, okay, these fancy brackets mean it's a set of these points. The domain is just all the x values, and the range is just all the y values. So the domain would be and most likely we should probably put it in order. -7, -6, -2, 3, and 8. The range, that one wouldn't necessarily have to be in order, but we can still put that in order, would be 2, 3, 4, 5 twice. Okay, now remember, it's alright to have two of these if we have the different inputs. So yes, it would be a function. Okay, so that's what we do on all of these ones. Same idea. So domain would be 9, 0, 4, 5, 2, 0, 3. Okay, so 0, 2, 3, 4, 5, and 9. The range would then be the y values, 2, 4, 0, 3, 7, -3, -1. Now, notice we have two zeros. So two inputs, check their outputs. Different outputs means it's not a function. Okay, on the next one, our domain 1, 2, 3, 4, 5, 6, 7, 8. So basically 1 to 8, right? We could write it like that, or 1, 2, 3, 4, 5, 6, 7, 8. The range, 2, 3, 4, 5, 6, 7, 8, 9. So we could go 2 to 9. You know, that would be appropriate, but we could also go 2, 3, 4, 5, 6, 7, 8, 9. Now, since we don't repeat any of these, the inputs or the outputs definitely is a function. Alright, so now we're doing it with some things other than points. So our domain here, how far left, how far to the right? Well, we've got an arrow here, so we're going to keep going to positive infinity. We start at 1, so 1 to positive infinity is our domain. Our range, how low and then how high, well, even though this arrow is very flat, it's going to keep going up to positive infinity, and we start at 0. 0 to infinity. Okay, number 5, the domain. Well, we've got here at, looks like 5 is our left to 0. Then it jumps from 2 to 8. So we'd go 5 to 0. Then because we jumped a spot, we do that little u and go 2 to 8. For the range, our lowest is -3. So we start at -3. Now we go up. Even though it jumps on the domain, however, it doesn't jump on the range. And we go up to positive 3. Okay, now 6 and 7. 6 is linear. Linear always has a domain of negative infinity to positive infinity. Same with 7, which is exponential. It goes from negative infinity to positive infinity. The range on linear also goes from negative infinity to positive infinity, because a linear, you know, plus 7, we'd start on a graph up here at 7, and then it would go down to that -2. So we keep going down, keep going up, keep going to the right, keep going to the left on this linear one. This exponential one, 3 times 5 to the x, would actually go up like this. This would be 3, then it's times them by 5. So it goes up to positive infinity, goes to the right to positive infinity, to the left to negative infinity. But down, it gets stopped by that x-axis. It's an asymptote. It's a point it will never go above, so it's 0 to infinity. Okay, number 8 says the elements in the table define the entirety of the function. So this just isn't a representative. The domain would be 1, 2, 3, and 4. So the range would just be 9, 98, 987, and 9,876. Okay? Because it's just those 4 points. So that's why we don't do 1 to 4 really. Alright, now for each function find the desired solutions. So, here's our function. This first one is our input, so we want to plug it in to t, so we replace t with that negative 4. Then we just solve. 2 times negative 4 is negative 8, minus 5 is negative 13. We don't touch this side, remember. That just goes down to give us our answer. So that's equal to negative 13. Okay, C is the same idea. Okay, it's the input, so I go h of 13 equals 2 times 13 minus 5. 2 times 13 is 26 minus 5 gives us 21, so h of 13 equals 21. Now this one gives us the output and we're working backwards. So I replace the h of t with 23 and then we solve for t. So I'd add 5 to get 28 equals 2t, divide by 2, we get 14 equals t. And if we look at part D, same idea. It gives us the output. So we go negative 33 equals our function 2t minus 5, and then we solve for t the same exact way. So negative 33 plus 5 would be negative 28 equals 2t divided by 2. We'd get negative 14 equals t. So if we're kind of thinking about all of these, they all make points. And, you know, we could make a table here of t and h of t, you know, with negative 4 and negative 14 and positive 14 and positive 13. Okay, because they all stand for those points. Alright, so now we're looking at using the graph to understand, kind of like we just did here, but with a graph instead of a function. So g of 2, that still stands for our input. Our input is always connected to the x, remember? The x value. When we talk about functions, there's two groups. The x values, the inputs, domain, the independent variable. Okay, those are all connected. So this input here of 2 goes on our x-axis. But because we are wanting to actually find it for the graph, g of x, okay, we don't want it to stay on the axis, we want it to go up and find where our graph is actually at. So we go up, and our graph is right there at 2. And because this is together, it actually wants the output, okay, remember the output is connected to the y, the range, the dependent variable, so we want the y value, which is 9. Just like back here, we plugged in negative 4 and found the output value. So on C, same idea, g of 0. So we go to 0, go up, our graph is at 1, so g of 0 is equal to 1. Once again, those are just like on a table of values. Now B tells us the output is 3, so we go on the y-axis because y and output are connected, go up to 3, but we want to find it for our graph, so we go to our graph. Now what's that x value? It's 1, so it would be 3. So actually, so if we combined all these points together, okay, we'd have 0, 1, 2, and 3. Well, why did I put 3 there? That was 1. Okay, so at 0 we're at 1, at 1 we're at 3, at 2 we're at 9. We don't have that 3. There we go. Now our explicit rule, well, we're starting at 0, right? So we'd go g of x equals 1. What are we doing to 1? Well, we're timesing by 3 each time, so we times by 3 to the x power. Okay, now we're looking at r of x, same idea. R of negative 1, so we go to negative 1 up to where our graph is, and the y value is 10, so it's 10. R of 2, we go to 2, go up, r of 2 is 1. So at 2 we are at 1 here, at negative 1 we were at 10. Now we want r of x equals 4, so our output is 4, we go to our graph, and our input is 1. So 1, we're at 4. So now how would we figure out this explicit rule? Well, it's linear, so we know we're adding, because it's a straight line. So from 4 to 1, we'd be subtracting 3. Well, if I go from 10, subtract 3, that's 7. Does that get me to 4? Yeah, so our starting number is 7. So r of x equals, we start at 7. What are we doing to 7? Subtracting 3 minus 3. How many times? X amount of times. Now, if we were to look at this, we could see that our slope was going down 3 to the right 1, which would make sense. And our y-intercept was 7, which is where that goes. Same with this one. Y-intercept of 1, and we're times them by 3 as we go. Alright, now on the set, we're determining if the relationship presented is a function or not, and provide a justification. So the distance a person is from the ground related to the time as they ride a Ferris wheel. So let's think about this. So here's a Ferris wheel. So you get in the cart and you start going up. Okay, so if we were graphing that, this would be our time on the Ferris wheel. This would be our height. Well, we start out, at the ground, and then we're going up, right? What happens when we get up here? We level out, then as time keeps going, we come back down, right? So, is it a function? Well, we have the same outputs, right? There and there would be the same height, but they're at different times as the time goes around. So yes, it would be a function. And it has to do with, because that time would be moving, we would never be having more than one output per input. Okay. Now, the amount of daylight during a day throughout the calendar year. So on number 13, we're thinking, okay, so we have the calendar, right? The days. And we get a certain amount of daylight in that day. And as the summer comes, that amount of daylight goes up. But as winter comes, the daylight goes down. So if I pick a day through the calendar year, is it going to have more than one amount of daylight? Well, if we're only dealing with a calendar year, so that means we're dealing with just 1 year, the answer would be no. Each day, they could have the same amount of daylight, but each day is only going to have one amount, which that makes it a function. Okay. 14. The value of a Volkswagen Bug convertible from time of first purchase in 1978 to now. So if we're thinking of this, we'd have all these years, right? From 1978 to now. And we'd want to know the value. Well, the value would be here, and it'd be going up, maybe it went down, up, That value could be going up and down, but if I pick a year, is it going to have a different value? That's the question. And you could argue, I guess, in 1 year, like in 2016, at the beginning to the end of the year, it could have a difference. So maybe there's multiple values in that 1 year. But if you're kind of thinking as time, this one, it kind of depends. I would say yes, just because it typically has the same value per year. Some of you might argue no, saying that in 1 year it could have a different value. So it kind of depends on how you justify it for that one. Alright, a person's name and their phone number. Okay, so here, it would kind of depend on which you called the independent and which was the dependent. Because if a name is independent, we can have the same name with different phone numbers, right? So 2 people named John Anderson could have different phone numbers, so that would make it a no. But if you flipped them around and had the phone number first, and then the name, unless you've got somebody in the same house with the same phone that have the same name, probably not going to be an issue, so that would be yes. So it would depend on which one you called the independent and dependent to determine if it was a yes or a no. Okay, the last one on this part, the stadium in which a football player is playing related to the outcome of the game. So this related to means the outcome would be like the independent, the x, would be the outcome, and would be the stadium. So I could have a couple different outcomes, right, with a different stadium, because they play all the time in those different stadiums. So this would be a no, because I basically only have two outcomes. You either win or you lose. And so this could have multiple stadiums, this could have multiple stadiums, which would make it not a function. Alright, so now we're going to take a look at talking about these features of functions. So we've got the domain, the range, if it's increasing or decreasing, the x-intercept, the y-intercept, the maximum, and the minimum. So I always like to start with the easier ones, the maximums, the minimums, and that, and the x and y-intercept. So looking at 17, easy to see our x-intercept, right? Negative 5, 0. Easy to see our y-intercept, 0, 5. Our minimum happens to be the same as our x-intercept, lowest point. Our highest point is right up there at 5, 10. Okay, now the domain. Well, we start here. Imagine that this is a bookshelf. This is where we'd put our bookend, and this is where we'd put our other bookend. So our domain of our graph goes from negative 5 to positive 5. Notice that our graph is increasing that whole domain, which would make our increasing interval the same as the domain. So it would never decrease. Now the range, we start how low it goes to the x-axis, and it goes up to 10. So it would be from 0 to 10. And there's our stuff for number 17. Okay, now number 18, we do the same thing. So, where's the x-intercept? So we've got two of them, which is alright. So negative 10, 0, and 10, 0. Okay, our y-intercept, that one actually represents a hollow circle, so it's not included. But it'd be down here. So 0, negative 4, because that's a filled-in circle. Our maximum, that highest point, would almost be up there, so it would be slightly below, since that's a hollow circle. It would be slightly below 3 and 6. So like 2.9, 5.9 would be our max. Our minimum is that point right there, so it would be 0, negative 4. Okay. Now our domain, the furthest left we go is 10, then we travel till we get to the y-axis. This is filled in, this isn't, and if we kind of smush these down together, those would overlap, so it actually goes until positive 10. Our range, we start down here at negative 4, and it travels up and is covered until we almost get up to 7. So this should actually be 6.9. I read that wrong. So it would go from negative 4 to almost 7, to that maximum. Now, with increasing and decreasing, we've got those multiple pieces. So it's increasing here from basically 0 to 3. Decreasing, we've got two parts. So it starts at negative 10 until we get to 0. Then it jumps until we start here at 3 to 10. And there's the features of functions for that one. Alright, 19 and 20, same idea. Okay, so we want the domain, the range, the increasing, decreasing, x-intercept, y-intercept, the maximum, and the minimum. So once again, let's start with our x and y. So x and y. So our x-intercept would be -1, 0. Our y-intercept would probably be about 0, 2.8 maybe. Or 1.8 actually, right? Doesn't quite hit 2. The highest point would be somewhere up here. I would guess right about there-ish. So that's like 1, 2, 3.5, 4. 3.5 and 4. And then down here it looks like it's right about there, which would be -6, -6.5, down to -7. Alright, now our domain. How far left? We start at -11 and we go until +9. Our range, our lowest is -7 and it goes up until +4. Where is it increasing and decreasing? Well, once again, we've got two sections of decreasing. So from here till that minimum, so x to x, so it would be from -11 to that minimum, -6.5. Then it would jump up to our maximum, which was 3.5, till we got to 9. Our increasing is just in between that, so it would go from -6.5 to +3.5. And there is number 19. Now, if we look at 20. So now 20 has an arrow, right? So it means it's going to keep going down to -infinity and to the right to +infinity. So there isn't going to be a minimum because it keeps going down. A maximum, that highest point would be right there because it stops, which is also our y-intercept. So those together are 0, 5. Our x-intercept would be right there and would be 10, 0. Our domain, we start at 0 and we keep going to the right to infinity. Our range, since we kept going down, we start at -infinity and go up until we get to 5. Now this is never increasing, so I could put the empty set there. So it's always decreasing, so our decreasing and domain are going to be the same. And there's our features of functions for that one. Alright, so 21, now we've got a story problem that we're kind of doing the same thing that we did with the graphs here and the functions. So now we're just dealing with it in story form. So Hope has been tracking the progress of her family as they travel across the country during their vacation, and she has created the function d of t equals 78 times t to model the progress they are making. So what would Hope be attempting to find if she wrote d of 4 equals 78 times 4? Well, her input, t, probably stands for time. So she's probably trying to figure out, I don't know if that would be hours, minutes, days. I'd probably say hours, or maybe days, since they're traveling across the country. But she wants to know, in that 4 amount of time, how far they went. So, for example, 4 days, how far did they travel? Okay, B, what would d of t equals 450 mean in this situation? Well, depending on what they're meaning, probably miles, they've traveled 450 miles. At that point, whatever the input would be would tell us how long. So what would d of 3.5 mean? Well, we'd be looking at how far in 3.5 days. And how could Hope use a function to find the time it would take to travel 800 miles? So basically, d of t would equal 800, which is kind of like b. So we use her function and replace d of t with 800. Then we would just divide by 78, and that would give us how long it would take. Which we get like 10.256410256. So basically 10.25 or 10 and a fourth. Days, hours, minutes, whatever she meant. Alright, now these last ones have to do with these functions. So remember, part A, f of x equals g of x. In other words, where do they intersect? That's what we're talking about here. So at this point, which is negative 5, 6, 7, 8, negative 8, positive 5, and at this point, 0, negative 4. Right? So where are our functions the same? That's what it's saying. Now, what is g of 0 plus f of 0? So our inputs are zeros. So the x is the input, so we start at 0. We go down. What are they both? Well, their y values are both negative 4. So we'd go, because that g of 0 means we want the output. So negative 4 plus negative 4 would give us negative 8. Okay, same with d. G of negative 8 plus f of negative 8. So we go to negative 8. Okay, and they're 5. They're both 5, right? That's their output. So 5 plus 5 would give us 10. Now in C, on what interval is g of x greater than f of x? So that g of x, we're essentially meaning the y values. So when is g of x greater than f of x? Okay, well if we look between those 2 points where they intersect, that's where f of x is higher, so that's where f of x would be. So beyond that, as we go to the left of negative infinity up until this point, negative 8, g of x is going to be bigger. So negative infinity to negative 8. Then we jump this section, and g of x is bigger again once we're beyond 4, negative 4, until we go to positive infinity. And there we go, guys.